Okay, here's question 13. It is a tough question, but definitely doable. You've got a cylinder that is emptying into a cone. So I've drawn my cylinder with its measurements, I've drawn the cone with the measurements, and all the water from the cylinder is going into the cone. So we can work out the volume of the water of the cylinder to start off with. So it's obviously pi r squared times h, which is a formula you're supposed to know, and the radius is 8, and the height is 25. So you've got 1,600 pi centimeters cubed of water inside your cylinder. Now it takes that water 40 seconds to flow into the cone. We're assuming that it's flowing at a constant rate because it hasn't said anything to the contrary. So the rate of flow is going to be 1,600 pi divided by 40. That's how much water is going to flow out in centimeters per second, and that's 40 pi. So that's 13a, that's the beginning bit. Then the next bit, it says, when the depth of the water is 10, find the rate of change of the height of the water. So we're looking for dH over dt. We're looking for the rate of the change of the height inside the cone. And we just found the rate of the change of the volume, so surely we're going to use it. So dH over dt is going to be a change of volume with time. And if you times that by change of height with volume, then we're going to have change of height with time. So we need to find dH dV, which means we need to find a formula of volume inside the cone in terms of height, and then differentiate it, and then flip it over. So the volume in the cone is going to be 1/3 pi r squared h, because that's the formula for volume in a cone. And that one should be given to you. And then I don't see how you can avoid similarity. If you look at the original cone, what you have is you have a radius of 15 and a height of 24, and it gives you a shape like this inside there, that triangle over there. And now if we look at the volume of the water in the cone at any specific moment, we've got a different radius and a different height. So basically, I'm using similar triangles, and it's really easy in this example. So because these triangles are similar, all the measurements are the same, the relationship between R and the side 15 is going to be the same as the relationship between H and the side 24. So H is this one here, and R is this one there, right? So this gives us this ratio over there, and then you can solve for radius. And so radius turns out to be 5h over 8. Now you have got a formula for volume, it's sitting right there, and all we need to do is put in radius. So instead of radius squared, we've got 5h over 8 squared. Then I've simplified it and just made it into this, right? And then I've done the derivative. So remember, the variable is h, so you're multiplying by 3, h goes down to 2, and everything else is a constant term. So when you finish sorting that out, it looks like this, right? So if dV over dH is that, then dH over dV is 192 over 7,500 pi. That's been cut off, but obviously you just flip it around. Now, right in the beginning, we decided we would use dV over dt, which they gave us from A, and then dH over dV. So this is, they gave us from A, we worked it out. This is what we just worked out now, and the rate of change of the height inside the cone is 1.024 centimeters per second. Last question. So they want you to find the rate of change of the surface area with time. It says to you rate of change of the horizontal surface area of the water. So that's a circle. Now obviously we're going to use some of the bits that we've used already. You might think, okay, dV over, let's use dV over dt because we found that in part A. Now that's not going to work very well, because then you'd have to have a formula for surface area in terms of volume. And you could do that. I mean, you could work out the surface area and you could work out the volume of the water, and you could make them equal to each other, and you could do it, but it's complicated. And I wouldn't do it if I were you. We just found the rate of change of the height over time, and that's going to be much easier to work with. So if we want surface area, we're going to look for the rate of the change of surface area with height. And finding surface area in terms of height is not a problem. So surface area of the circle is pi r squared. We know that r is 5 heights over 8, so we can stick it in, and this is a volume for surface area in terms of height. We can then differentiate that, and we'll get dSA over H. And then it says when the height is 10 centimeters. So I'm going to say, I'm going to go back here and say this one over here, which is dSA over d height times by what we worked out in the previous one, which is d height over d time. And we're going to put those in and work it out, and that gives us 8 pi. They didn't say to work to exact numbers, but it makes sense, and no doubt the original questions did say that. I hope that's okay.